in the following ways practical transformers do. First of all, their windings have got some resistance. Secondly, the cores aren't infinitely permeable. Thirdly, the flux produced by the primary is not completely captured by the secondary. There's leakage flux and vice versa. The iron core produces eddy currents and hysteresis losses, which contribute to the temperature rise of a transformer. So what we need to do now is develop a model of a real transformer that will take account of these attributes. Yeah. So what we're going to do is build a conceptual model where these losses can be represented by, we do that by adding components to the circuit.
Look at these, I know.
And then you look at the head. Sorry? Do you have to do it? Yeah. Right? So, I mean, I've taken a leap of faith there and put it all up in one go for the ideal transformer with an imperfect core. Okay? So, once you do an example, it's not too bad. Right? So, what we've got up at the moment is got a generator. Let's just put this magic pen up. That work? Generator. Yeah. Now, when the idea here is a real transformer will draw current even if you haven't got anything connected to the secondary. So that's what we're looking at first, is to represent the current that's being drawn from a transformer, and the primary is connected to a voltage, but nothing's connected to the secondary. The secondary is open circuit. It will draw some current. That current is what's heating the windings up, yeah, magnetizing the core, all right, and causing the eddy currents to flow in that core as I see up and down. It's a loss. How can we represent that? Well, the core of a transformer isn't ideal. It's not infinitely permeable, and there are hysteresis losses. Eddy currents flow in the core as a power loss in the form of heat. So when we're open circuit, there'll be a current flowing in the primary coil, I.O. That's this current here, flowing, even when there's zero current in secondary. Yeah. Then what we do is we split that current into the current through this resistor Rm. Okay, that represents the heating effect in the windings, the heating effect of the core, and it represents this heat power loss here. Yeah. And then this current through here, through Xm, represents the magnetizing current. That's why it's an inductor, because it's the current taken to magnetize that primary winding. And that will flow regardless of whether there's anything connected to the secondary side. Okay with that so far? So it's made up of two components, Im and Ir. All okay so far? So it looked a bit daunting with all the numbers and letters and bits and pieces, but actually that's an inductor and a resistor in parallel. Alright, and remember they're not real components. There isn't an inductor in that circuit. It's an inductor representing the inductance of this coil, the primary side coil. Alright? There's a resistor representing some imaginary resistance components that are going to cause that transformer to heat up. Yep. So, looking at that in a little bit more detail, right, Rm represents the ion losses, the resultant heat produced, which causes the in-phase portion of IO to flow. So thus here, it's the IR current. It's current through a resistor, therefore it's in phase with the generator voltage. There's the generator voltage. The resistor current is in phase with it. Okay? Then we've got the current IM flowing through an inductor. Okay, there it is. 90 degrees out of phase. Okay? See, IVIL, inductor, current lags downwards the voltage. Alright? And then the overall current IO flowing there is represented by the phasor addition of those two, and that's got an angle in there, the phase angle. Yeah? So that phasor diagram, the three red ones represent the currents, and there's the generator voltage, EG there. Okay? Everyone happy with that? Yep. And again, we always check with this. Make sure that's what you think it is. By the way, this diagram, I've got a couple of dots on it, and dot notation says that when current's flowing into that dot, current's flowing out of that dot, it just indicates polarity for our transformer. Okay? All happy with that? Yeah? So, we'll have a look at an example and how we can do some calculations. A large transformer operating at no load draws an exciting current, and that doesn't mean any exciting current, it means the current that excites the magnetic field as a term. Yeah. And it is of 8 amps, and the primary is connected to a 400 volt 50 hertz source. So the primary side is connected, but it's not under load, so nothing connected to the secondary, exactly as we've got it. For the wattmeter test, it is known that the iron losses, so the wattmeter says this transformer is using 500 watts off load. Yeah. Calculate the reactive power absorbed by the core, the values of Rm and Xm, that's the little resistor and the little inductor representing those losses, and the value of IR, IM and IO. Alright, so have a little bit of a think for a minute or so about how you might start that problem. So that's the circuit. Knowing what we know there, what can we find? We've got generator voltage, 400 volts. We've got a power, and we've got a voltage. Sure. Correct. bit dangerous, that 8 amps at the moment. I'll see why eventually. What formula do we know that involves, remember, what's always associated with in terms of power? Remember them 3 different powers we got. True power. What type of component uses true power? Resistors. Yeah? So we're looking for Rm, and we know E, and we know and we know P. So what formula do we know relating power, voltage and resistance? That's current and resistance, current and voltage. P is equal to, sorry, better not go with V yet, Eg squared over Rm. Therefore, Rm is the generator voltage squared over P. 400 squared over 500. What power type, what power value could I use the 8 amps with? The S. We haven't been given S though, have we? That's why I said it's a bit dangerous to use the 8 amps at the moment, because that's a combined that's the combined current of an inductor and a resistor. Yep. Yeah, so that's going to have an angle involved with it that we haven't been given yet. Yeah. So what the answer of that come out to? 320 ohms? Now we know that, what can we find that we're being asked in the question actually in part C that could be useful to us? Yeah. So therefore, we can find IR, that is equal to what voltage is across it, the generator voltage, (400) over 320, 1.25 amps. You just, these look daunting, but you've got to work through them a little bit step by step and find out. RM, yeah. Deliberate mistake, Aaron. As you know, I never make deliberate ones. Alright? Now this first part is actually find the reactive power represented by the letter Q measured in var. Yeah. So if we look at this triangle that we've always been associated with. There's Q, there's P, there's S. Yeah? So we need to get to two values. We've been given that one, P. How can we get S? The units give it to you. $3,200 VA. So now we've got two sides of this triangle, 3,200 and 500. Therefore, we can quite easily find the reactive power. Therefore, Q is equal to the root of S squared minus P squared. Good old Pythagoras' theorem. Yep. That's the square root of 3,200 squared plus 500 squared equals. Just check with your calculator, but I got 3160 var. All right. So this, go back to here, this inductor is 3160 var. Yeah. That's got a 400 volt supply across it. Yeah. So where we used this formula with P, the voltage, and RM, and rearranged it to find RM, we can use another version of that, Q, that voltage squared, but underneath XM, and rearrange it to find XM. And at the moment, you notice we're ignoring any angles at the moment because we don't need to worry about them, because all we're talking about is the magnitudes of these things. Nothing about phase angles at the moment. Alright? So, we can go that also Q is equal to Eg squared over the inductive reactance. Therefore, Xm is equal to the voltage squared divided by Q. That is 400 squared over 3160, and whatever that comes out to. 50.7 I got, so have you rounded that? Alright, 50.6 then. Ohms. Yep. So far, we've found, looking at A, B and C, we've found the reactive power, Q, there. We've found XM, there. RM earlier, Okay, we've found IR. Know what I find? IM. How can I do that? Is it R? No. Lastly, IO is equal to, by Kirchhoff's current law, IO, this current, total current flowing, is them two added together. What? Is IR plus IM. But what have we got to do? What we got to be careful of here? Now we got to bring the angle in. Yeah, because they're not in phase with each other. Yeah. So IR, let's look back at your notes. IR is equal to what? Angle associated with that, 0 degrees. IM, 7.9. Angle associated, sure. CIVIL, lags, minus 90 degrees. To add them together, we need to do what? No, minus 7.9 J, isn't it? Yeah. And the other one, IR, 1.25, angle 0 degrees, converts to 1.25 plus 0J. Therefore, IO is equal to these two added together, 1.25 minus 7.9J amps. Now convert it back. See what you get. So we've looked at the situation when the transformer's off load, right? Now, when we connect a load to the secondary and a current flows in a secondary coil, because we've neutrally induced a voltage across the secondary, within the secondary coil, the current flows, we then got a whole different situation. We got a flux set up in the primary coil, okay, and that induces a flux in the secondary coil, and they're all interacting with each other. Okay. We've got flux in the primary coil that's linked with the secondary, doing useful work. We've got flux in the secondary that's linked with the primary. Yeah. And then we've got leakage fluxes in both coils. We've also got the resistance of the secondary to consider as well. It's going to cause some more heat losses. Yeah. So I don't want to get too hung up in that diagram, because all that's saying down here is that total flux created by the primary is made up of flux that's linked plus the flux that's lost. The total flux in the secondary is made up of the linked flux, take away the flux that's lost to the air. Alright? I'm more interested in you understanding how to analyse that than I am getting too hung up about that complicated diagram. Okay? So we've got a portion that's nicely linked and doing the transformer operation, but we've also got some flux that's leaking away in both the coils. Okay? So, how do we represent that? Two mutual fluxes can be combined into one, shown above, the two coils having their own leakage fluxes as shown. So, the stuff that's linked is linked in both of them. So we combine that together, and these two fluxes here and here are the leakage fluxes. They're not linked with each other. Yeah. We got, this is ideal, number of turns, E1 and E2, same as we had before. Alright? Again, I don't want to get too hung up in this maths down here, okay? Because I'm more, like I said, I'm more interested in the practical analysis of the transformer, and I'm worrying too much about that. Alright? So, what we do is we represent the two leakage fluxes by having our ideal transformer in the middle. There's our primary terms, N1, N2, flux, all of it linked. Move the leakage flux away. We're going to represent that as a series inductor in the primary side, representing the leakage flux. Okay? And the same over this side. We're taking the leakage flux away from this coil and representing that. We're going to represent that as another coil in series. Yeah. So the two leakage fluxes represented by two further coils, one in the primary, one in the secondary, that are not linked. These two coils produce voltages that are not subject to the transformer process from the primary to secondary. So they're like losses that don't get transferred from one side to the other. So the voltage that's dropped across this does never get across to this side. It's not linked. Alright? So we can now model, and I've added a little bit further. Right. These two terminals here are the actual primary terminals that you can put your voltmeter on. Right? They're measured. That's where we connect the generator voltage to. This inductor there, XF1, represents the leakage flux in the primary. This resistor here, R1, represents the resistance of the primary windings. So that's representing some heat in the primary windings. Okay. Here's our ideal transformer of ratio A, our number of turns on the primary and secondary, and here's our E2. So that bit is our ideal no loss transformer in the middle, and then we got this inductor here representing the leakage flux in the secondary, and this resistor represents the resistance of secondary windings. These two terminals, again, are the secondary terminals that you can put your voltmeter on and actually measure the voltage. Okay, and then that's our connected load. So anywhere here, you cannot do measurements on a real transformer and find those values. All right, we're going to look at it. There's a way that you can get to find out what those values are from a real transformer by doing what's called a short circuit and open circuit test, and then you can calculate them, but you cannot put a voltmeter on and measure them. Those components, remember, don't actually exist. All right, it's just a model. Everyone reasonably happy so far? All right. So we could calculate, all we're saying here is we could calculate the value of that from the primary voltage divided by the current. We could calculate this inductance by the secondary voltage divided by the current, and the same with R1 and R2. All right. Should be noted that in each winding, the resistance and the inductance combine to make an impedance Z1 and Z2. So we can combine these two values together into one impedance with a magnitude and angle if we want to or need to. All right. Lot to take in, I know. Been a long session. Won't be much longer. So what we're going to have to do is have a look at an example of how we can analyse that situation. Secondary winding of a transformer possesses 180 turns. When the transformer is under load, the secondary current has a effective value of 18 amps at 60 hertz. The mutual flux has a peak value of 20 megavabers. I'm not keen on this example, if I'm honest, but we'll go through it anyway. The secondary leakage flux, theta F2, has a peak value of 3 megavabers. Calculate the voltage induced in the secondary winding by its leakage flux, the value of the secondary leakage reactance, and the value of E2 induced by the mutual flux. M. Right. We'll move on to better examples. So that's your full now transformer model. Includes everything. So we got our leakage flux and winding resistance. Yeah. Leakage flux and winding resistance in the secondary. And then we got our iron losses and magnetising current represented there. Yeah. Okay. So that's the full transformer model, Richard, with the iron losses represented, as well as the leakage flux and winding resistance. So we wouldn't need to add anything more to that to do any kind of analysis of a transformer. All right, and I've already said EP and ES, there and there, are the only two voltages you'd be able to measure. Right, in your notes, you've got an example 3 on page 11. Have you not? Right. We'll do this example. I'll quickly draw it up on the board. Right. Yeah. I've written nom in there, the nominal ES, i.e. the stated secondary voltage, 400 volts. Okay? That's what the nameplate says. So that's 11 kV down to 400 volt transformer. Yeah? And a nominal rating of 100 kVA. So those two come from the nameplate. They won't be what you actually get. Alright? So, what can we find from the information that we've been given? One key piece of information that we've always had in most of our examples so far, have I not given you? Yeah, that's one, but there's another something even more in terms of ideal transformer. Aye. Is there a way we can get the ratio here? We know, right? So let's go I. We know that I is equal to N1 over N2, right? But we also know that N1 over N2 is equal to E1 over E2, or I2 over I1, right up the front tonight. So we can get A from any of those three things that we could find on the nameplate. Probably not going to tell you how many turns it is, but from the nominal voltages or the nominal primary and secondary currents, and they're always going to give you these two, we can get the transformer ratio. So that's 11,000 divided by 400. I'll make that 27.5. And that's the difficulty. I'm sure that's what you're on about, Richard, isn't it? Where the bloody hell do I start with this problem? Yeah. You understand what I mean by the term nominal, don't you? That's the stated. Never actually happens in real life, does it? That's all sorts of variables mean that it doesn't happen. Right? but it gives us what the ideal transformer ratio is. If that was 100% efficient, that's what we would get. If we put 11 kV in, we get 408. It gives us our ideal turns. Yeah? I don't know how you go about trying to remember that sort of thing. Only you'll know the things that'll help you remember them. Okay, we'll go over it as many times as we possibly can. But at the end of the day, that's practice. Alright? So, full load current. There's a second thing that's asked for. So we're asking for I2, full load. There's current flowing in here. If that's full load, and we want to know the resistance and ZR, or ZL, sorry, that draws it. So, what is the full load current? And what resistance value would cause that full load current to flow? So from the information you've been given here, how can we calculate that current flowing in there at full load? Nominal kVA, yeah, nominal S. This is the nominal S, and it's equal to the nominal voltage times the current. So if we rearrange it, we can find the full load current. IFL is equal to S nominal. Hang on, let's do it a bit better than that. Let's make a statement that S nominal is equal to I full load times E2 nominal. Therefore, IFL is equal to S nominal divided by E2 nominal. And S was 100,000, wasn't it? Divided by 400 equals 250 amps. So, if this transformer was ideal in every way, and we connected the right load to a maximum current in the secondary, is 250 amps. Yeah? All get that? Yeah? Now we can use that current to find the resistance that would draw that current in that secondary. Yeah. Therefore, ZL is equal to secondary voltage divided by the secondary current. That's 400 over 250. 1.6 ohms. Oh, yeah, 1.6 ohms. So we can now analyse that full load situation. Somebody connecting that 1.6 ohms to that transformer. What actually does it draw? That won't be that full amount because of the losses involved that we haven't taken into account yet. Because we just used the nominal values. Okay? This technique that we looked at earlier, transferring impedances, okay, to find, so we're going to find the value of these secondary impedances there, and there, when they're transferred over to that side. We need to do that to do our analysis, because we don't know this voltage here, because there's losses in that side. All right, so we can't analyse that transformer like that. We've got to use the transferring impedances method. ZL. Yeah. So, C. How do we transfer ZL across to the other side? How do we transfer impedances? And I was now do that for the X2 and the R2 values. So X2 dash is equal to I squared X2 27.5 squared
22.69.
times
Oh, you're doing that, sorry. That was 40 hours now, isn't it?
0.03
Yeah.
equals, what did you say, 27 points?
22.69.
22.7 ohms. Yep. And then this one is A squared R2, 27.5 squared times 0.008 Yep. Okay. So we can now transfer those. We've transferred that, so we can draw our circuit with all those components on the one side of the transformer connected to the 11 kV input. So we can go like this. E.g. (11 kV) R1 12 ohms, X1 36 ohms, R2 dash was 6.05, X2 dash 22.7 ohms, ZL dash in there, what was that, 1,210 is it? Yeah. and our transformer ideal is over here doing nothing at the moment. Yep. And we'd have a current flowing here, I1, that is also equal to this current here, I2 dash. Yeah? And we have volt drops across each of these components, some or all of which we may well be able to calculate. We just got one circuit now, no transformer involved, so we can actually calculate the values that we want, and then if necessary transfer them back using the reverse process. Right? So what did I put for D? Primary current. If fully loaded transformer is supplied with its nominal voltage. So I want to find this current here. So we transferred values involving full load, because that's what we want to know. Yep. I want to find that current. So what do we need to find first? Total, I'd rather you modified that a little bit. Yeah. ZT. Yeah. If we're going to add them together, what form do we want them in? Rectangular. So we could we not, add together all the real parts, R1, R2 dash, ZL dash, yeah. Because that's what we do. And then all our imaginary parts, x1 plus x2 dash multiplied by j. So kind of jumped a step. If that's really causing anybody any problems, say so, and we'll do it individually. But that's effectively what you'll do. The two resistors, the three resistors are per resistors, and we just add them up, and there'd be no J parts associated with them, right? The two inductors are inductors only, so they'd have no real part, but they'd have parts. So we just add the resistive parts together, the inductive parts together, all in one go. Anyone really struggling with that concept? Yep. So that is 12 ohms plus 6.05 plus 1210 plus 36 plus 22.7 J ohms. Check it please. I make that 1228 plus 58.7 J ohms. There's a chance as we could need it in either form eventually, so let's have it in transferred form as well. I make that 1229 ohms angle 2.73 degrees. Yep. All right. So now we can use that. Therefore, primary current I1 is equal to EP over ZT 11,000 over that 1229 angle 2.73 degrees check it, but I make that 8.95 amps angle minus 2.73 degrees. Does that fit in with civil? Inductive, negative angle. Right? E. Secondary current I2 at full load. Looking at our diagram, where we got the hook into I2, well, we got how can we hook in to know to find the secondary current on the original transformer diagram? Look at my labelling. Think about what circuit you've got there. We don't know, we haven't got I2 labelled, but got I2 dash labelled. What's that current equal to? Same as I1, isn't it? Because that's only one series circuit. That's why we do all this. Yeah? So we can now go I2 dash is equal to I1. Yeah? And I2 is equal to A times I2 dash from earlier. Yeah, we transfer the current to that side, we divide by A, so to go back again, we must multiply by A. So that equals 27.5 times the I2 dash current, 8.95 amps angle minus 2.73 degrees. Wish I'd learned to start my calculations. You'll have enough time, don't worry.
Yeah, something.
The exam is 10 hours. Or
So the exam, would this be something like you'd get an exam then?
Sorry?
Would this be something like you'd get an exam?
You could do, yeah.
Yeah?
Yeah.
This sort of level, this
Yeah.
is what you'd get, yeah?
Yeah, get practicing.
So you would recommend practicing this question a million times before July?
Plenty of times.
Yeah.
I won't be exactly like this, mind you,
It
but
would be 26.5 instead of 27.5. Got you.
Yeah.
I might be step down up instead of step down, for instance.
Then I'll
Yeah. Which means that number will be, Richard,
fraction.
less than 1, yeah? Less than 1, yeah? So that I2 is, according to my calculation, 246.1 amps, angle minus 2.73 degrees. So that's the current that we get in the real current in the secondary, because we now transferred it back. That is quite substantial. The thing is, I might not ask you, I'm going to write a question that you can do in the time available. I'm not stupid, am I? You know, but I might not ask you all these things.
Half an hour is going to be scratching ahead, so you've got to remember that.
Yeah.
Do you know what I mean?
No, well, I
Right
can't.
now, panicking.
Yeah.
10 minutes crying.
When I went to the exam yesterday, I was like, oh my god, I can't believe it. My heart's going. I was actually quite nervous once I actually got in there and sat down. I was like, what's happened? It was quite calm until I went to bits or something. Fan was blowing my pages, isn't it?
What I do want, lastly, I just want to do, remember we talked about the nominal voltage of secondary, we used 400 volts. What do we actually get after these losses? So,
Well, it stays there. I always write on the old book, or no jars.
so we're going to find ES at full load. So what we need to do is find this voltage here, this voltage here is E2 dash, yeah, E secondary.
ES secondary back.
Yeah, that's the one that you can measure at the terminals, isn't it? Remember? Because that's the voltage across the load. So we're going to find that and transfer that back to find the actual secondary voltage at full load. How can we find that? We know the current going through it, I2 dash. We know the value ZL dash transferred. So we can find it. We can find E2 at full load. E2 dash is equal to I1 times ZL dash. That's 8.95, angle minus 2.73 degrees, times 1210, angle nothing, because that's a resistor. One thing I won't give you guys is inductive or capacitive or complex loads on these transformers. You already got complexity anyway from the leakage voltages and leakage inductors. So I'm not going to make it more complicated still. All right. The answer to that is 10830 volts, angle minus 2.73 degrees. That's the secondary voltage transferred to the primary side. Yeah? So you can see we're putting 11,000 volts in. You can see already lost some. Yeah? You already see you lost some. So now we've got to transfer back. E2 is equal to E2 dash over A, that's 10,830, angle minus 2.73 divided by 27.5 equals, and if you just check it please, but I make it 394 volts, angle minus 2.7 degrees. So the transformer itself doesn't create a huge power factor issue, 2.7 degrees, yeah, but we've got a loss there of phenomenal of 6 volts, yeah. And the way they'd do that regarding design is they'd nudge it with the number of turns on a secondary. So on big power step up, step down transformers, you'd select a suitable tapping to get the voltage at maximum load that you wanted. They'll put multiple tappings right near the end of the winding, and you go on the tapping you want. Yeah, so there's an adjustment on in the design. They'd adjust that on number of turns.